Hello? Hello, Amer. Do you hear well like this? Okay. Thank you very much. So, if one of the persons here are connected to Slack, so you can tell me if there is any question during the lecture, or if the sound is lost or something, because here I don't get the notifications. Well, there will not be problems in the first minute, but I wrote like a couple of minutes ago one message in the PE room in Slack. I wrote a couple of minutes ago a message in the PE room, and Amer answered it. So this is the active room now. Let me do a little test. Check if I can write in the whiteboard. This camera goes here, and so I can use the whiteboard, all of this until here. No, a bit less. Yeah, this green pen. Don't see anything with this red. Yes.
Can't find the Slack channel.
You can't? You can't log in?
No, I can log in. I can't find the Slack channel.
Okay, so is the channel is not in the course press Slack, it's in the general Slack.
Yeah.
Oh.
Yeah,
Oh.
I'm in course press. What is the course? What is the channel name?
But it's not in the course press Slack. It's in another. It's in the general Slack.
Okay.
And now, with the camera, we are back. Okay. We can start. Okay. Today is the second lesson on the performance evaluation block. On Wednesday we had our first lesson, and on Wednesdays we saw how to create performance models in the queuing network language. Today we are going to see how we can obtain performance results from the information in these models. We are going to see the operational loads. On how to get results from this model and from the kind of information we get in the about the system, there are two lessons. Today with operational loads, and on next Wednesday using a tool that simulates the queuing network. Okay, why separating in two blocks? Because if we can evaluate the performance the performance metric in which we are interested using operational laws, we are going to be much faster and accurate and much more general for the system. Because the operational laws are simple equations which may be used as an extra representation of the average behavior of almost any system. So they do very few assumptions about the system. They can be generalizable to almost any system. But they give information about average behavior. That sometimes is good enough to know only the average, the mean. Sometimes we need some other information. So these laws are very general and make almost no assumptions about the behavior of the random variables characterizing the system. In the next lesson, we will see how other times we care about the random variables that characterize the system. But today, in the operational laws, they don't do any assumption about this. And the laws are simple. They can be applied quickly and easily. You will see that each of the laws is like a multiplication or a multiplication and a division. So this, and we will see 5 laws. And these laws are based on observable variables. So if we see how a system is working, we have already the inputs to apply the operational laws. Now, let's see what can we observe from a system that will be inputs to the operational laws. So as we saw, the same cloud we saw on Wednesday, arrive request to our system in this cloud, and at some point, the requests from clients are served and they leave. So if we observe this system, we can measure the following quantities: the time we are observing the system, the number of arrivals, A, C, the number of completions. If we are not losing any request, these values will be the same. So everybody who asks something to the system will get an answer. But if we are losing jobs inside the system, they might be different. B, we call this the total amount of time in which the system is busy. So this B is lower or equal than T. If B is equal to T, it means that the system has been always busy. There was always some client to serve. The rest of time between B and T is the time that the system is idle. It's ready, but there are no users. And the average number of jobs inside the system, and we call this N. We saw on Wednesday that this system may be composed of subsystems. So like there were like 4 last day. So this same 4, and we knew how to create a queuing network from that. So the same information we can measure to the from the system, we can measure for each subsystem. And we will use the subindex K for each subsystem. So now you will see like 4 more metrics that are sub K, that refers to K 1, 2, 3, and 4. So again, T, the length of time we are observing the system or each subsystem. A sub K, the number of arrivals to the concrete subsystem, K. Ck, the number of completions we observe in this subsystem K. Bk, the busy time, the total amount of time in which the subsystem is busy. And N sub K, the average number of jobs. So the same characters, letters we used before with the subindex K, it refers to each subsystem, and without subindex, they refer to the.
And does the total amount of like B, how long the system is busy, need to always be inferior than the T, which is the time we observe the system? Like B inferior than
Yes.
T.
Yes.
What if the system is always busy?
If the system is always busy, the busy time will be equal to T.
Ah, equal.
Yeah, lower or equal, yeah. Before there was a lower, no, lower or equal. So from these observed values, A, C, B, T, can directly compute some quantities. Like if we divide the number of arrivals to a resource by the amount of time we have observed the results, we know the frequency with which arrivals come. So if we are 10 seconds looking at a resource and we see 10 arrivals, we can see that in average there is 1 arrival per second, and this is the lambda. X, the throughput. So if instead of the arrivals we look at the completions, we see how many jobs have been completed in the amount of time we have observed, we can see the frequency with which we complete jobs. The utilization refers to the time that the system is busy. So we divide the busy time by the total amount of time, we get the proportion of time. So 20 seconds out of 40 seconds of observation, the utilization 0.5. The service time refers to the time that each job needs to complete in a resource. So how can we compute this service time? If we look at the amount of time that the resource has been busy, and we have the number of jobs that it has executed during this time, we divide these two values and we see how much time each job needed. The number of visits to a resource for each job that completes in the system. So for instance, this resource can get more than 1 visit because a request arrives, executes 1, executes here, then it returns, it's executing twice now, and maybe can leave. So the number of visits to a resource is not fixed to 1, can be lower than 1 or higher than 1. Lower than 1, for instance, if we have this possibility, the number of visits of this maybe is like only half of the jobs go here, because the other half take the other route. And we compute this mean number of visits, dividing by the number of completions in this resource by the number of completions in the system. If this resource has executed 20 jobs and the system has produced 10, it means that for the system, for producing each job, it has to execute twice here. It has to visit 2 times this resource. And when a resource is not visited 1 time, fixed 1, that is what usually happens, we can differentiate between the service time and the demand time. So the service time is the time that needs each visit, and the demand time we multiply by the average number of visits. So we can compute the total demand time for each job in the system. So if a job needs 0.5 seconds in each visit, and we know that it visits twice to complete, we can see that from this part it needs 1 second. We have here an example. If we have the preview system and we concentrate on the resources, we are observing it, and we observe it 26 seconds. And we are going to see when each job arrives and the number of jobs in the system. So we see that in second 0, there are 0. Second 1, nobody has arrived. In second 1, 1 job arrives here. In second 2, second 1, nobody has arrived. In second 2, 1 job has arrived. In second 3, nobody has arrived and nobody has left. Second 4, another job arrives. Now we have 2 jobs in the system. In second 5, nobody has finished it and nobody has arrived. In second 4 arrives, it's 4, 5, and in second 5, 1 leaves. So the first one that had arrived has finished it. So instead of 2, we have again 1. In second 6, nothing happens. In second 7, the other job finishes. So now we have 0. In second 8, nothing happens.
Is like the same behavior for jobs?
Yeah, for these operational laws, they look at the average and they don't make almost any assumption. So only this.
Because if it's a priority, like one job, like when it comes to the system, it's not doing anything, right? Until the other job is finished.
Yeah.
The service.
So yeah, this does not assume if the first one that left
Yeah.
is the first one that arrived or the second. Doesn't matter. For the average, doesn't matter.
So and this is like calculating like inside the service, like inside the system, or like in the buffer of two. Like
We are observing this part of the resource.
the whole thing.
Yeah.
Okay.
So in this, and in the end, we have this information. So during 26 seconds, we have seen that there have been up to 3. So here are the values we need, like observation time, have been these 26 seconds. We have observed 7 arrivals. So this, every time that we change to an upper level. So the first, the second, the third, the fourth, the fifth, the sixth, and the 7th. We have seen also 7 completions every time that the graph goes down because one is completed. So here, the first, the second, the third, the fourth, the fifth, the sixth, and the 7th. The system has been busy 20. 20. So we have observed 26, and we have idle these 2, and these 2. So these other 5 and these, right? They are 20. So from this observation, we can compute arrival rate, the number of arrivals divided by the amount of time. So 7 divided by 26. The throughput of the system, the same. We have produced 7 during 26 seconds. The utilization, the system has been busy 20 seconds out of the 26. And the average service time, we have been busy during 20 seconds, and we have been able to produce 7. So its job needed like 20 divided by 7 seconds of. So this, we are going to start with the first load. A simple multiplication. So utilization low. The utilization of a resource is the throughput of the resource multiplied by the service time of the resource. And this is the proof. So these are what you, in the rest of the slides, what you see here in red are the equations that we have showed before. And using what you see here on the left, we will derive the load. So we have seen that the utilization of a resource was the blocking time divided by the total amount of time. Now if we multiply and divide by the same amount, by 1, it remains the same. Now if we change this, we get, instead of B divided by T and C divided by C, we get CK divided by T times BK divided by CK. And this was the throughput that we had seen before, and this was the service time. So in the end, the utilization is the throughput times the service time. If we have these two pieces of information, we can easily compute the utilization. So the example, if a server is completing 40 requests per second and each request requires 20 milliseconds of service, the utilization of the server, 40 times 0.02, which is 0.8. So the server is busy 80% of time. In some resources, we saw that we could have, in some service center, we could have more than one resource. And on Wednesday, we call it the C character. So if we have more than one resource, the utilization is the throughput times the service time divided by the number of resources. The example, if we go to a gas station and we measure that the gas station is serving 4 cars per minute, And the gas station has 5 pumps. And we see that each car needs 45 seconds for service time, for refueling. The utilization of the gas station, if we work in minutes, throughput 4 per minute, service time 0.75 minutes, 45 seconds is 0.75 minutes, divided by 5 pumps. So the gas station is at its 60% of capacity. It still accepts more cars without creating very long queues, but if we can also compute what is the limit of cars that we could serve, and if we see that there are more cars, maybe we have to invest in putting more pumps.
So the U, which is the frequency, I think, is like changes if we have more servers in the system, or more. Is it?
Yeah. Well, if yes, if
Resources, more
I-
resources to
yeah, if we add resources, the average utilization is lower. Yes. So if we have a completely busy processor, each second executes a task that requires 1 second. And now we put 2 processors, so one time executing one processor and the next time the other, then processors are at half of the capacity. It's half of the time the processor will be idle and half of the time will be busy, in average. So this is the first law. Second law, service demand. Now we see 2 different computations to relate to the demand. This is the first one we show in the definition. Like if we know the service time, service time was the time that a job needed for its execution in the resource. But if it needed more visits, we said we are going to compute the demand. That is the service time multiplied by the number of visits. So this was the previous definition. So this is equal also to the time it is blocked by the number of completions in the system, or also equal to the utilization of the resource divided by the throughput of the system. So if you have any pair of these, you can compute the other. So using also these are both derived, the D to this part and the D to this other part. These are the equations we saw before. So we saw the demand was the number of visits times times, not divided by. Here it is correct. But we,
The formula there is correct.
yes, here it's correct and here as well, but here I did it wrong. So then we know that the number of visits to a resource is the number of completions in this resource divided by the number of job completions in the system. So we can substitute this by this block.
What's the V again?
V, number of visits.
Number of visits.
So we substitute this V by this, and then we get this 2, because this is the same as the block time, by this law. So it remains that the block time divided by the number of completions is the demand. That is the first part of the law. And for the second, we use this other 2. And in the end, we start from the previous derivation. We can multiply by t and divide by t, so by 1. Now we change these 2 t's, and it remains bk divided by t, and it was the utilization before, and t divided by c, that was the inverse of the throughput, the system throughput. So, yeah. So it remains like utilization divided by the throughput. So using this demand law, we can compute like what is the demand if a server is completing 2 requests each second and the disk is used 80% of time. What is the disk demand? So this utilization 0.8 and the system throughput 2. So the disk, we can say that the disk demand is 0.4. And if a disk service takes 100 milliseconds, so every time that a job goes to the disk, it needs 100 milliseconds, how many times the job asks the server, which are the mean number of visits. So if we know that for its full service needs 0.4 seconds of disk, and that each service takes 100 milliseconds, means that it makes 4 visits to the disk. Using yeah. So the demand, we know the demand 0.4, then this gives the service time, and we can compute the number of visits. So this was the second law. The third law, Little's law, which is named after John Little, and it says that the mean number of jobs in a system is equal to the departure rate of jobs times the average time jobs are in the system. We will work with this example that is the same one we saw in the beginning, like 26 seconds, 7 arrivals. And an example of what can we know here with this law, like if we go to the presbyter to ICA, to the door, and we count people who are coming, the frequency, so we see that they are coming 10 people per minute. And we measure how much time they are inside, so and we see that each people takes 5 minutes to leave. How many people are inside ICA without looking? Hmm?
How long is duration are they staying? We measure it, right?
They're staying for 5
Yeah.
minutes.
Yeah, we say now the frequency already. Instead of saying we have seen 10 people, we see 10 people per minute.
Every 5 minutes.
Yeah, 10 people per minute, and we see that they are inside 5 minutes. So we can say that there are 50 people inside ICA without counting in average. So in this, how to prove this? We are going to define a variable W that counts the accumulated time in the system by all the jobs. So using this example, in the 26 seconds, the accumulated time is 36, which is like the summatory of everything or the integral if it were continuous. So 1 plus 1 in this second, plus 2, plus 1, plus 1, plus 0, plus 0, plus 1, plus 2, plus 3, plus 3, plus 3, plus 3. So in the end, it makes 36. This is the time that all single job has accumulated in the system. And the average number of jobs in the system, if we know the amount of time that all jobs have accumulated and the amount of time we have been observing, it's like calculate the average of this. So the previous value, the 36, divided by the amount of time we are dividing. So we know the average number of jobs in the system. So with this, we get 36 divided by 26 as n, using like the common sense. Now we are going to check if this is the same as the x time r. So this, we got w divided by t. If we multiply and divide by the number of completions, it remains the same. Now if we change this by this, we get the number of completions divided by t, which is the throughput, first term, and the accumulated time divided by the number of completions. That is the average time a job resides in the system. So if we have that the system accumulated time is 36 units. And we have been able to produce 7 jobs. Means that each job has been in the system 36 divided by 7. So this is the R. So using the first common sense, we got 36 divided by 26. And using this XR, the X is the completion 7 divided by the observation time, 7 divided by 26. And the R is the 36 divided by 7. So in the end, we obtain the same. So this law is true if we prove it in this way. So this is the third law, the fourth law of the day, forced flow law. This law shows the relationship between the throughput of different components within the system. It states that the throughputs or flows in all parts of a system must be proportional to one another. So the throughput of a concrete resource, the K, is equal to the product of the system throughput and the visit count. We want to see how the frequency of job completions of a resource. We get the frequency of job completions of the system, and we multiply by the number of visits to this resource. And using these 3 previous formula, we got like the throughput, n is equal to the visits divided by multiplied by the system throughput. Right. This was part of the first one, and we can say that Ck is equal to Vk times C, and then we get these 2. This is the system throughput, C divided by T. So with the system throughput and the number of visits, we can compute the components throughput. And with the component throughput and system throughput, we can compute the number of visits. So an example of this, if a server completes 2 requests per second and each job requires 4 visits to the disk, what is the throughput of the disk? The server is the system, so it's the system throughput, and each job requires 4 visits. The throughput of the disk, 2 times 4. So the disk is completing 8 jobs each second. Now, another example for the forced flow law. So you see that is a formal application of this, but then you could also think that, okay, by common sense, I would have done the same. But now you see a structured way to apply the same. So if we have a robotic car factory, we are producing cars. And producing each car requires 6 services of a robot that puts the windows, to put each of the 4 on the sides, the front and rear. And then 4 services of another robot, the one that puts the door. And we have observed the factory, and we know that the robot that places the windows is placing 120 windows in an hour. And we would like to know how many doors per hour is putting the robot that puts the door.
120 is the throughput?
The throughput of the window robot.
No, the whole throughput. It's 120. You know that the robot, but that's it. Oh, it's one component.
Yeah. 120 windows. We know this. The robot of the windows, 120. We know that it has to execute 6 times. So we are producing 20 cars, 120 divided by 6 per hour. And then we apply to the component of the windows. We are producing 20 cars per hour, and we will have to put 4 windows. So the throughput of the robot that puts the windows is 80, 20 times 4. So this you have in the slides. The process as well. So each windows is the throughput of the robot that puts the windows. V windows is the number of visits of the robot that puts the windows. X doors, the throughput of the robot that puts the doors.
Where did we get the 20?
20 cars per hour. So first we use this for the robot of the windows, and this from the robot of the windows that we know, so 120 and 6 windows, to compute this X, the system throughput. 120 divided by 6, like we are creating 20 cars per hour. And then we apply these 20 cars that we have computed to the robots of the doors. So now if we are producing 20 cars per hour and you have to operate 4 times for each car, you are operating 80 times per hour. This is the first flow law, and now the last law that is quite similar to little law, and it's called the interactive response time law. This is the example we saw on Wednesday. The population is a bit higher and the delay a bit lower. But users make a request that goes to a web server, then to application server, then to a database, then come back to think. And we want to know the response time. And the response time should cover this. My think time is not response time of the system. So we have to tune a bit the liters law to remove this part. Because if we apply directly the liters law, we will compute all the cycle time. So in the end, is compute all the cycle time and remove this part.
That's little law is without interactive system.
Yeah. Well, if we apply here little, we would get the the time to do all the process. But the response time in which we are interested is only this part. So in the end, it's little minus this. So we are going to call this thing time the Z. So here, 200 seconds. So if we cut that little, told us that the number of jobs in the system was the throughput multiplied by the residence time, that would be all, and in this case is the R in which we are interested, plus the think time. And now we want to compute only this, so this R. First we move the X, n divided by X, and then we subtract the Z, and we have the R. And this is n divided by X minus Z is the interactive response time.
So what's the think is the response time?
Yeah.
Well, that's the think time is just the interacting with the user, and the rest of the system. That's the system response. That's the system working time, busy
Yeah.
time.
Response time. The response time considers both the time that is receiving service and the time that is waiting, because somebody else is receiving service. So the response time counts everything since the user does the request until the answer is received. So the time that is waiting here, the time that is getting service, then the time that is waiting here, the time that is getting service. And let's do an example of this. Well, 11. Now we have seen all the laws, and we are going to do 3 exercises. We can do them after a break. 10 minutes break. Yes. Well, I'm going to check Slack if there was any doubt. Amer, Lucian, Jacob from our online participants. Do you have any question? Yes. Okay. Will the recording? Yes. Yes, yes. I thought it was not necessary because I was able to find it without directly from the course press. But yes, I will put a direct link. Sorry, I forgotten to do it on Wednesday. I didn't know it was necessary. Sorry. So if there is not any other question, we are going to have the 10 minutes break now. Okay. here we are back, and I remove the microphone and I put it again. So if we can confirm that everybody can listen to me decently. Jacob, Amer, Lucian. Jacob. Yeah, thank you, Jacob. Okay, now in the second half of the lesson, we are going to do 3 exercises where we use the operational laws we have seen. So we get expertise with this. And the third one will be, is more or less the size of the assignment, last year assignment. And last year assignment was expected to be like 3-4 hours for the student. So what you see in the exercise 3 is like more than you will be requested to do this year. So you can have an idea of the size of the assignment. So first exercise, we have our system modeled with a queuing network already. It's the same as in the first lesson because the web server executes 10 per second. The application server each resource can execute 2 per second, and there are 2 resources, and the database can execute 2.5 per second. Population 400 users and delay 200 seconds, the think time. Now we have observed how this system behaves during 1 hour, so 3,600 seconds. And we have seen that 7,092 requests have finished it. And this is not the first question. Up to here. What is the system response time? So it seems that we will need to use the interactive response time law. See, close. We are asked by the system response time. Let's see. The interactive response time law. Say that the response time, mean number of jobs divided by the mean throughput minus Z, the think time. Large enough for yeah. We have, yes, exactly. We have the number of users, actually, the N, the 400 people. And the number, and the throughput, because these 400 people have executed 7,092 requests in 1 hour. So 7,092 divided by the number of seconds in 1 hour is like 1.97, yeah, 02 request per second. And we have the think time as well, the delay. Z was 200 seconds. So we apply the law, and the response time is going to be 400 divided by 1.9702 minus 200. Which is 3.04 seconds. Now, second question. What is the resource that is closest to saturate? Let's put again the camera with the system, the queuing network. We know the system throughput. The resource that is closest to saturate is the one that will have the utilization highest, the highest utilization. So we are going to compute the utilization of each resource and we will get the maximum. We have the utilization low and the force flow low. Because we need to compute the mean number of visits to each resource for each execution of the system, and then we can compute the utilization of our resource by the throughput of the system and the service time.
What's inside the service? What does that represent?
What is the
Inside the service, in the red, what does it represent?
the service time, service rate?
Service rate.
So the mu in the previous lesson was service rates. That is the inverse of the service time. So this 10 is like it can execute 10 per second. So the service time, 100 milliseconds.
Okay.
The service time of this, 0.5 seconds. And the service time of this, 1 divided by 2.5, so 0.4 seconds.
So wouldn't the one that has like the lowest service rate be the one that's the closest to saturate? Or am I wrong?
In this case, first when we compute the average number of visits, here is quite easy because all of them receive 1, 1, and 1.
Okay.
So the number of visits to this is 1 for each execution, for this as well and for this as well. So once we have the number of visits, we can use the utilization low and we relate the service time, the throughput of the specific element with the service time. So I'm going to do it put again here. First we use the forced flow low that it tells us that the throughput of a resource is equal to the number of visits to the resource multiplied by the system throughput. Here we know the system throughput. If we observe the system, we see that this is 1 for every service because every time that executes, it has to execute once in the first queue, once in the second, and 1 in the third. So it turns out that the throughput of each component is the same as the system throughput for all components in this exercise. And now we can use the utilization low and we get that the utilization of a resource is equal to the throughput of a resource multiplied by its service time and divided by the number of resources if there is more than 1. So from this we get the first resource, the web server, throughput 1.9702 multiplied by the service time, which is 0.1 seconds, and we'll have 0.197. So 90% of utilization. For utilization of the web server. For the application server, we have 197.02, the throughput, times the service time, that is 0.5 seconds, divided by the number of resources. We have 2 now. And I don't know, the result is in the next slide because this division is not so immediate for me. Yeah. Thank you, 0.4925. Utilization of the application server. And the database, we apply again, the throughput of the database is 1.9702 times 0.4, and only one resource, so divided by 1 is equal to 0.788. This is the utilization of the database. And now I realize that there is a limit here for the camera in what we are streaming. So the last part, for people here in the room, I'm going to repeat this up. So this last is on the slides. Maybe they are looking at the online people are looking only to YouTube and then to the slides. So 87.02 times 0.4 was equal to 0.788, and this was the utilization of the database. So what is the resource closest to saturate? One is like 20%, the other around 50%, and the database almost 80%. So the database is the closest to saturate.
Just one question.
Yeah.
Before I told you, can't you just tell this by the rate, the service rate? Because since it's a linear system, like the whole.
Yes.
We don't have to calculate all of this just if we have the service rate, because we will know the one that has the
yes.
The highest.
Yeah. So instead of computing the numbers, if you know that you are multiplying everything by the same amount, you can get the service rate and the number of resources. Yeah.
Because it's like it has the most services.
Yes.
It's
Yeah.
the one that will be saturated.
Yeah. Exactly. This actually the next question maybe goes in that direction. No, in some way. Yes. So you could say that this part is able to serve 10 per second. This part is able to serve 2 times 2, 4 per second. And this part, 2.5 per second. So which will saturate first? The slowest. The one that can serve less per second. Yes. Absolutely. Alternative way. Yeah. No, it's fine. We will use it later, actually, in the next questions. So what is the percentage of time that users spend waiting? So if we are having this company with our 400 people using the system, that was a document system, and we have seen that they think 200 seconds, so 3 minutes and something, and then they interact with the system, and they have to wait for the system to answer 3 seconds. The percentage of time that users spend waiting for our system is like this 3.04 divided by the total cycle time, 200 plus 3.04. This is 1.5%, more or less. So with this system, we are wasting 1.5% of time of the employees. If it were faster, maybe they would not waste so much time. If some resource goes close to saturate, we will see examples in the last lesson. This response time could grow a lot, and like instead of 3 seconds could be 80, and then the users, the percentage of waiting time is much more, and you feel that the people who are working with this system spend half of the working day waiting. So in that moment, maybe you can also think that you have to upgrade your system because you are paying a lot of people for waiting in front of the computer. What would be the maximum throughput of the system for infinite users? So if instead of 400 we have infinite, what is the maximum throughput that the system could achieve? Here is when we use the reasoning you had done before, that you didn't need to compute the utilization of all the resources. So if we have infinite users, like there are always people who want to execute, this can produce 10 per second to this one. Even if 10 per second are arriving, they will queue here because this can produce 4 per second. And this one sends 4 per second, but this one can only serve 2.5 per second. So the maximum throughput of the system,
2.5 times 70,092.
well, throughput, if we are in frequencies, this is already a frequency, so 2.5 per second. The minimum of how much each one produces. Here, because we are counting that, is also only one visit. If this one had only like half of the visits, then even if it is can produce up to 2.5, it only receives half of the visits. So the bottleneck would be somewhere else. So actually, the next question, if instead of having one resource for the database, we add another one, we have seen that this is the bottleneck, the database, and we decide I'm going to consider to add another database and have 2 resources, so balance it.
5 per second.
Good. So good starting. Good 5 per second. So the database can produce now 5 per second if we add another resource. But then the maximum throughput of the system would be, the bottleneck would change here because it would be the minimum between 10, now 5, and 2 times 2, 4. So now this would be producing up 10 per second. This would take and release 4 per second, and this could accept up to 5, but only arrive 4. So in the end, the throughput of the system would be 4 per second, because we have changed the bottleneck from the database to the application server. If we add another resource to the database.
Oh, if you add another resource to the database can process 5 requests per second. But the bottleneck shifts to the application server because its throughput is less than the database now. So that's why we can only process 4 per second.
Second exercise. We are asked to determine the average system response time for an interactive system, again with the following characteristics. 25 users population, think time of 18 seconds, 20 visits to a device, to a service center for each interaction with the system, so the number of visits is 20 for this device. This device, we have observed that it has 30% of utilization. and the service time for each of the 20 is 25 milliseconds. So first, we model the system. Using a queuing network, so we get more training on modeling with queuing networks. Oh, this is super. Interactive system, so we'll have here the waiting, the delay, and it says that the n is going to be 25 and the set 18 seconds. Then they go to a device that has service time of 0.025 seconds. And at some point it will return, but it also says that we execute 20 visits. So here, when one job finishes, it may restart again, actually in average 20 times, and then it will finish. So this is the model. Now the question is to determine the average response time. So this, the interactive response time, low, like n divided by x minus z. So r and the number of users divided by the throughput minus z. We have n. We don't have the throughput, and we have z. So we are going to see how to compute the throughput using the forced flow law and the utilization law, and the rest of information that we have, like 20 visits, 30% of utilization, and 25 milliseconds. So well, the solution is in the next slide. So if you can see this better, I don't write it in the whiteboard. Hmm? Yeah. Yeah. And we know the utilization, and we know the service, so we can find the throughput of this device, and it's 12 because the utilization is 0.3, and the service time is 25 milliseconds. So we have this device is producing 12 per second. And then if we apply the forced flow law, if we know that this device is producing 12 per second and it's visited 20 times, then the system throughput, the division. So 12 divided by 20, we have 0.6. So this was the last x, because we have the n 25, we have the z 18, and now the x will be 0.6. So the interactive response time, 23 seconds, 0.7. Now you can see how in this response time, the time spent waiting instead of serving becomes, because how much time has been serving? The demand of the device. And this was the number of visits multiplied by the service time. And we had 20 visits and 25 milliseconds of service time, which creates 0.5 seconds of demand. So executing inside the circle has been only 0.5 seconds. But instead, it has been here 23.7. So 23.2 has been waiting because other jobs were using the system. So this is an example where the waiting time is much more than the actual execution time, the demand. Okay, and the last exercise. This is the kind of description you can find in the assignment, but this is longer. So because this one has 6 elements that are more or less the number of elements in the assignment last year. But I'm referring a lot of times to the assignment last year because I will publish it, so you can try during the Monday or Tuesday before our assignment. So this last exercise, a company uses a client-server application for the management of its resources. The system is architected with 3 tiers. The first tier includes 2 web servers that share the workload. The second tier includes 2 application servers that provide complementary functionalities, and both should be visited for its access, for its execution of a client request. And the third tier is 2 database servers that share the workload as well. So first question, describe the system with an open queuing network model and considering a single service center and without the network delay. So let's what is expected from this? The first tier includes 2 web servers. So the request arrive, and we will have web server 1, 2 web servers that eventually share the workload, and web server 2, and they share the workload. So some will be here and some will be there. The second tier includes 2 application servers that provide complementary functionality. So both have to execute. So when they finish either here or here, they go to the application server 1, and since both have to execute, then application server 2. Like this, yeah. And then this. Database 1 and database 2 in the third tier because they share the workload. You could say here you are assuming that the application server 1 executes before the 2, the second. Yeah, it would be if this come like this, would be we will get the same results and it will be as good as. So it's a decision you take, and it will not have an influence in the final results. But yeah, it's a question that you don't specify which one executes first. Yes.
Like at the top, that's DB, that's application server. No?
Did I what?
Like you could write just for the model. The last 2 are for database. The 2 in the middle are application.
So if I could draw what?
Like just at the top, so you know these 2 are database. It's like you did in the other model before, like in other slides. Like for example in slide 29.
29.
It's not important. Like you could
Okay.
That's web server.
Yes. Well, I use the initials, but
I can see.
so WS1 and WS2, web server 1 and web server 2. This I try to put the names like this. AS application server, AS2 application server 2, DB1 database 1, DB2 database 2. So this is our model. And now, in order to evaluate the performance of a system, a 30 minutes monitoring phase has been performed. And we have collected some data about the system completions, the service time of all the 6. So we can write them here. Like this S is equal to 0.1. Service of this is 0.1 as well. Service time of this is 0.15. Service time of this is 0.2. And service of this is 0.25. And service of this is 0.25. And yeah. Service demands. Additional information. The web server 1 and server 2, so the demand of this is 0.2. The demand of this is 0.2. The demand of the application server 1 is 0.75. The demand of the application server 2 is 1.7 seconds. And the demand of each of the databases is 1 second. It's not very clear, not very big in YouTube, so. Now we can see, where is the black here? If we have demand higher than the service time, it means that we are going to execute more than one. So the number of visits will not be exactly 1. So this means that when it finishes, there will be some chance that it restarts here. And the same happens, this one, the demand is higher than the service time. Because here the same, so it may happen if we have a demand of 0.75 and service of 0.15, it means that at least executes 5 times. So 0.15 times 5, 0.75. So there will be some chance that it comes back, and the same happens for the other. So in the end, we had these loopbacks because the demand is higher than the service time, and this is a way to model it. So that's why you can see in the slides that all come back. So questions in this exercise. Compute the system throughput during the measurement phase. Service throughput. We had also some more important information. We had seen 30 minutes and 450 completions during these 30 minutes. So we had defined that the system throughput is the number of completions divided by the amount of time we had observed in the system. We have seen 450 finishing in these 30 minutes, 1,800 seconds, 0.25 requests per second. This is the system throughput. the mean number of visits to each service center. We had a demand, the demand low. The demand of a service center was equal to the number of visits of the service center multiplied by the service time of the service center. And we have the service and the demand of each service center, so we can divide the demand by the service time and we will get the mean number of visits. So in this case, 0.2 divided by 0.1, the number of visits is 2. Throughput. This is the same, the number of visits 0.2 divided by 0.1, this is 2. The number of visits of this is 0.75 divided by 0.15, this is 5. The number of visits, this 1.7 divided by 0.2, that is 8.5. And the number of visits of the databases, 1 divided by 0.25, 4. And this also 4. Is the results in the next slides, but this is how. So using the service and the demand that we know and applying the demand load, we get the number of visits. So compute the utilization of all the servers. We had another demand load. Let's say that the demand is equal to the utilization of the resource divided by the system throughput. And we know the system throughput because we have calculated it before, and we know the demand because it's one of the inputs. So the we will multiply the demand by the throughput and we get the utilization. So for each resource, so demand times throughput, 0.2 times 0.25, 0.05, right? Yeah. This is the same, so the utilization of this is going to be 0.5. Utilization, the demand times the throughput. This demand 0.75 times 0.25. So the utilization of this 0.185, 1875, and so on for the rest. Now it's going like too slow, too small. If I write the rest, it does not help a lot. And this is 0.05 for this, 0.18 for this, 0.425 for the application server 2, and 0.25 for the databases. All the throughputs. Now the throughputs are xk. You can apply the utilization law. First, let's say that the throughput will be the utilization times the service time, and then also the force flow. Let's say that the throughput is the number of visits to the resource times the total throughput, the system throughput. So we know this is the 0.25. We have calculated the utilization before. Oh, this is the number. Sorry, this is a B. Yeah.
We do it for each component.
Exactly. The number of visits we have computed it in green. So this we have this normal green again. We have this number of visits for each, and we have the total throughput, the 0.25. So we can compute the throughput of each resource. And we can also use this one because we know the service and the utilization already of. So either using this or using this, we should get the same results. So for application server 1, 5 visits times 0.25, the throughput following this 1.25, and the throughput following this other, the utilization is 0.1875, and the service time 0.15, and it goes on. And it goes something that is not. I check later. Check later if it is a division. But this is the last slide. This was the last comment. So we have enough information for computing in two different ways.
Is this like how the type of exercise we get for the exam viewer?
Yes. So from this description and some observations, you will have to compute or service time or utilizations or something, most probably service time, because in that way you can put a service time for the queuing network. So maybe you get the utilization and the throughput and you don't get the service time, so you have to know that there is a law that relates these two concepts, so you can compute the service time and put it in the queuing network.
Can take like 20-30 minutes to do one exercise? Like
Well, now we have done 3 in 45 minutes.
this one in 45 minutes?
We have done 3 in 45 minutes now.
Yeah, so we get like 3 like this?
No,
Or
1.
just
1.
Yeah.
Just one.
One smaller than this.
Okay. Yeah. It's
So
doable.
if we have used 15 minutes for doing this, but I had already the solutions, so it has been we have been a bit faster. And the exercise will be smaller, so instead of 6 different service centers, maybe there are 3 or 4 only. So you will spend also 10-15 minutes doing this computation.
Even like this, it's like it's just using rules.
Yes, yeah.
The law.
Yeah. Certainly, it's more knowing which is the information you know and how each part of information relates to other, and what can you compute having some other part, because then the laws are multiplication or a multiplication and a division. So it's
I think it like to be much easier if I have all the laws in front of me, like if I write all the laws or have them like open in the web.
exactly.
Yeah.
Yeah, and if you had studied before, because now you have learned then and you have got the assignment, yes.
Yeah.
So, but during the assignment you can have the laws in front of you. Yeah,
You're allowed to have the slides open.
It's an online.
it's yeah. So, I will
All day.
Yeah,
I think we'll
like-
stay here till midnight.
I will be here 2 hours, but it will close at midnight, so people can do it at home and using the material. Well, yeah, you guess that the chapters that are also in my Moodle are chapters from an online open book, so you can find them. It's published openly, but I collected the interesting chapters, so reading them before the assignment, so you get also the same view of the operational laws. I explain it here. It's in the chapter. And then for the assignment, having maybe the slides with the 5 laws that we have seen, and so you know which one you should use in each moment. You know which one fast. So you read the assignment and you can decide which one is in 1 minute. If you read the assignment and you have not studied anything and you have to start studying then what each rule means, you will need more time. And if you have not studied anything, maybe you will need more than 1 day and you cannot finish the assignment. But if you are already familiar with the content, it should be this part in 10-15 minutes should be done.
Study there
Yeah.
too. It's really good assignment.
Well, if there are like 4 service centers and each service center needs 1 or at most 2 operational laws to get the result you want to compute, it's a multiplication. So you can spend 1 minute thinking about which is the operational law you need, and then 20 seconds doing the multiplication, and you have the result already. Any question in Slack? We have finished it. I'm going to do some zoom here so you can see some of the results, and they remain here for some seconds. So you want to rewatch the video, and if there are no more questions, thank you for the participation, both to here on campus students and online students, and see you next Wednesday. If you have further questions about the assignment, don't hesitate asking me, because I have been answering now some questions, but I think I didn't repeat the question, so maybe you heard some answers, but you didn't hear the question. Okay, bye-bye.